So the whole idea about the chapter is your force there, your momentum will change. There. If momentum got changed, means got acceleration. So you want to find the force, you can take change in momentum over time. Or if you have the acceleration, you can take mass times acceleration. That's the gist of it in a nutshell. Okay. So now we're going to dive into this idea of momentum, but we're going to focus on the acceleration here. So we have a rocket that is stationary on a launch pad. So let me draw a rocket. Miss Lee draw rocket. Miss Lee's rocket will look like a house. Okay, so we have maybe the rocket will have like some dome shape. Because normally they will slowly by stages, they will shoot out the fuel tanks, right? So then it will take off. Okay. So at t equal to 0, the engines are switched on and the exhaust gas are ejected from the nozzle of the engine. So if you remember that Walter Lewin physics lecturer with a colorful shirt one, he sit on the bicycle and then he pull the fire extinguisher and then the fire extinguisher shoot gas out. Like fart. Teacher, I got student ask me this before. If I fart hard enough, does it mean that I can move forward? Can. You just need to fart very hard. Maybe you won't have a butt after that. But if you shoot gas out, exhaust gas, okay, and then the rocket will accelerate upward. The rocket will move here. So let's think a bit. The gas is being pushed downwards. So there is a, change color here. There is a force of the rocket on the gas. I will push the gas down. But Newton's third law says, if you push me, I must push you back. So the rocket pushed the gas down, the gas will push the rocket upwards. So here, there is a force of the gas on the rocket. Okay, and this graph gives you an idea of how the acceleration of the rocket changes from 0 to t1. So the rocket will accelerate and then plateau. So here the acceleration is increasing, and then here the acceleration is constant. So if I want to cut into two stages here, I can write acceleration increases. And here, acceleration constant. Okay. So once we interpret the graph, and they ask you to define acceleration. Okay. So to define acceleration, this one is just a simple matter of fact to say that this is the rate of change of velocity. All right. How much or how quickly velocity changes. This is the formal one. But for IG or for your level, you don't want to write the most complicated one also can. You can just write this one as change of velocity over time. Or you can write change of velocity per unit time. Okay. If you go back to your notes and this part here, acceleration, it's change in velocity divided by the time taken for the velocity to change. Okay, next part. Sketch a graph to show how the speed of the rocket changes between 0 to TF. Okay, I want to do a quick sketch of the acceleration graph at the side here. Your AT graph just now was increased to a maximum and then stay the same. So when your acceleration increases, it means that imagine you accelerate, your foot is on the accelerator of a car. You press your accelerator down and then you hold it there. So the velocity or the speed will start from rest. We turn on the engine. We will accelerate until a point here. Let's say this point is t. So this point here is t. So you could also use gradient to help you, because currently A is equal to gradient of speed time. So if acceleration is the gradient of speed time, this portion here, the gradient is bigger and bigger. I mean, this value is bigger and bigger. So from here to here, A increase. This means gradient increase. So you can tell from here to here, gradient is getting steeper and steeper. Okay. Then we reach this point. So at this point, the gradient will be constant. You just draw a straight line. And now, actually, I should draw not so big. Anyway, that would go to T1, not enough space. Gradient decreases, okay, until it reaches the maximum value, T1. After that, it increases at a constant rate, okay, something like this. So as long as the graph is connected, a bit particular, the graph is connected, doesn't look very weird, then can the reading. So here gradient increase. This part here, gradient stay the same. So here's also 顺便 revision for the first part. Gradient the same. Because A the same, constant. So this part here, gradient is constant. So this sketch is 3 marks. Okay, this part, basically you draw the speed increasing, you get 1 mark level. You simply draw something like that. Okay, anyway, it's like don't leave empty lah. It's the what's that word? 安慰奖. 安慰奖 first mark is speed increase from 0. Okay, second mark is this part here, increasing gradient. And then the third mark is here, constant gradient until T1. Okay, each section, each mark. And then if you generally draw the velocity increasing from 0, then okay. All right, let's continue. Sometime later, the rocket is far from Earth. Wow, space travel, very good. The effect of Earth's gravity on the motion of the rocket is insignificant. 就是讲呢, gravity already so far away from Earth. It's like there's no gravity. Okay, so as the rocket accelerates, the momentum increases. Well, because when there's acceleration, B increase and momentum P is mv. So momentum also increase. So state the conservation of momentum. So I would say the total momentum of a system remains the same or remains constant. Total momentum, no change. If you go back to your notes, it will be this part here. No change in momentum condition if the net force is 0. Yeah. So from here, I could write the total momentum of a system remains constant if there is no, or provided there is no net external force. Net external force on the system. Part 2. Explain how the principle of conservation of momentum applies to the accelerating rocket and the exhaust gas. So before this exciting thing happened, the momentum of the rocket is 0. So I guess maybe we can look at a rocket, traveling away, or a rocket launch. Just to make sure that share sound first. Okay, let's observe the rocket launch lah.
All systems are go. We're about 90 seconds from the launch of Space Shuttle Discovery.
They're checking all the system one by one.
T-minus 60 seconds and counting. We are transferring to orbiter internal power at this time. Discovery is now running off its 3 onboard fuel cells. Coming up on a go for auto sequence start. And we have a go for auto sequence start. Discovery's onboard computers have primary control of all the vehicle's critical functions. T-minus 17 seconds and counting. 15, 12, 11, 10, 9, 8, 7, 6, start, 2, 1, booster ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
Okay, I think you get an idea lah. So as the rocket goes up, the gas is being pushed down. So if you think about the initial momentum, right, at this stage, what is this momentum? 还没有启发之前, the momentum is 0. So when it is lifting off here, the gas momentum that is downward must be the same as the rocket momentum that is upward. Then they will cancel off to become 0. Okay, but very cool one. Teaching why so many gas. I say, Lord, you must have a lot of gas. If not, you cannot lift off something very heavy. Okay, so we are going to compare the momentums before the explosion and after the explosion. Okay, so I will first point out that the initial momentum, or rather, accelerating rocket and the exhaust gas. Okay, so I guess in this case, because they asked us to start from here, I think I'll start here. As the rocket accelerates, the momentum increases. Okay, so I will say the rocket gains upward momentum. Okay, this is because the ejected gas, okay, gains the same magnitude or the same quantity or the same amount of momentum in the opposite direction. Hence, the total change in momentum is still 0. Momentum is conserved. All right, so momentum still stays the same. The rocket 上去的时候，这个 momentum will increase. Let's say this momentum plus 10. Plus 10 unit lah. I don't know what the unit is. Okay. Because actually it's like probably plus a lot more than 10. Then the gas shoot downwards. So gas that is being shot downwards have a momentum of negative 10. So the magnitude is the same. 10 and negative 10. But in the opposite direction. So the total change is still 0 because plus 10 minus 10 is 0. Ma. These are all vectors, right? So the direction matters. Okay, so the rocket will gain upward momentum and the ejected gas will gain the same magnitude of momentum in the opposite direction. So change is 0, momentum is still conserved. Because there's no external force. Gravity is in 不在的. Okay. So if you're wondering what about this one, this one got gravity, right? This one. Yes, this one got gravity. But if I shoot out enough gas, I can overcome gravity as well. Okay. But that will be another question for another day. So for your practice, please try these questions. Okay. I teach you some you can't find answers. So you have 1. Need to go to the shooting ring. 2. How to go shooting ring? You see MRT. 3. You only got 3 more questions to do. And no, wait, 4. There's also 69, the arrow thing. So you have 4 questions. To try to do them and submit them by next week. Can I? You know, right? Because I need to, okay, I'll show you something. I need to write that report. So I would like to see your work so that I can write a report. Because I need to write a report about how you're doing. So if you diam one in class or never reply, I also don't want to force you. So yeah, do some work so I know you're alive and not just a bot. You are not a bot. You can click on all the picture with a traffic light. Okay. So we're going to move on to the next thing pretty soon. But yeah, you do the rest. Okay. You can review the work that we have done so far. If you need help, it's only 4 questions. You got this. Okay. So, today we're going to level up and talk about energy and work. Probably it's not a new idea to you, the idea about energy, work, and power. Okay. And we are also going to talk about the different types of energy resources. I want to show you the whole thing now. Quite low so one. Okay. And also how to calculate power. All right. So in this unit that we'll probably spend maybe about 3 weeks, I'm thinking. Okay. We're going to recover or rediscover what it means to have kinetic energy, gravitational potential energy, chemical energy, elastic energy, nuclear energy, internal energy, because an event or a process has happened, right? And then we will also look at how to calculate energy using equations. I will list them down for you. And then we will apply conservation of energy. Okay. We also understand that all this energy must come from somewhere, right? So we will 顺便 take a road trip to figure out where all the sources of energy comes from. The advantages and disadvantages of different types of energy. Certain types of energy are pretty okay for the environment. Certain types of energy is just no good. Okay. And after that, we will look at the equation. Like actually, whenever there is transfer in energy, there is work done. So work done is energy transfer, and then we're going to use the calculation. So for your syllabus, right, we don't just do core, we do core and supplement. Basically, it's the whole thing now. Okay. So that's where we'll stop. And then next week, maybe we'll take a look at power. All right. So I think energy is not new to you. 一定看过 energy, right? So we're gonna look at it now. So we're gonna look at your Stephen Hopper book in page 81. Okay, so I will rearrange the syllabus a little bit to kind of fit the narrative that I want to present this to you. Sec. It's number 56. Okay. Number one, in the big picture that we have done so far, because we are dealing with forces. So far, we know forces does a few things. For example, it changes motion, meaning it changed momentum. Okay, and then we have the whole, because we change momentum, we got F is equal to ma. Okay, but also change in momentum, which is impulse. So force is also change in momentum over time. So we spend some time in this region. Okay, the second type of forces, second type of effect of forces is that it will change shape. I think we have done this before this, but I would just like to remind you, maybe, let's say, for example, you apply the force on the spring and you stretch the spring, there's a change in shape. Okay, but a consequences of this change in motion or change in shape is that there is also a change in energy. For example, if we think about the rocket just now that we discussed, the rocket is accelerating, right? If you look at the speed of the rocket that we draw just now, wow, the rocket speed, bang bang sang like that, then like that. Okay, so if we think about this rocket speed, the velocity increase, then I can definitely say, not change in acceleration, change in velocity. I can definitely say that there is a change in kinetic energy. Because kinetic energy is the energy of an object that is moving. Okay, and for example, you could say, teacher, the rocket getting higher and higher. Oh yeah, so simple rocket. Okay, number one, change in velocity. Number two, change in height. So if there's a change in height, surely there is a change in gravitational potential energy. So it's not 有这个就没有这个, it's more like 一起来的. If your motion change, there is force. And if your motion change, there is probably a change in velocity. But not just that, we also may have changed height. So that will cause a change in gravitational potential energy. And in this case, whenever you change shape, okay, there is also probably a change in elastic potential energy, the energy stored in the rubber band. So in this chapter, we will go through each type of energy one by one, learn to identify whenever there is a change. I'm going to guess that you already have a hunch, and also understand that actually the main character is the fact that there is a force. The force started all of this chain reaction. Okay, so part one. That's the overview. So first thing we're going to look at is work done. Okay, W. So in everyday language, we say work done as you move something, or you travel, you apply a force of a certain amount to your object. So I'm gonna refer your textbook for this. Okay. So I'm just gonna write down in the POPLE author textbook. This one is Cambridge. Publisher. I'm looking at page 84. Okay. So work done. Let's say, for example, you have an object that is traveling a certain distance, like so. So you have this one. Okay. So work done is whenever we say 1 joule of work, or we apply a force of 1 Newton, and then your object travel a distance of 1 meter. Okay. So in short, work done can be calculated by the equation force times distance moved in the direction of the force. Okay, you have to make sure the F and D is parallel. Sometimes they will purposely confuse you one. They will say, oh, Amina is walking up staircase. No. This is my friend Amina. Teacher, why her staircase so high? Wanna find. This is my friend Amina. Okay. She walks up the staircase. This is your change in height. This is your distance. Teacher, why leh? Because when she walk up the staircase, who is she fighting against? Fighting gravity, lor, mg. Mg is the one that she's fighting against. So work done by our Amina here will be mg times t. Now parallel. Okay. So this actually means F and D are parallel. Then they can just trick you a bit and say, oh, this staircase is 2 meters. Okay, so a bit 夸张了. A. It's not mg over A, it's not mg times 3A, nothing like that. You take the vertical height. Okay. So whenever we think about energy, work done causes a change in energy. For example, when Amina climbs staircase, okay, this W is work done by, okay, I'm going to call her A. Work done by A. Okay. But there's obviously an energy conversion from one form, convert to another form. So definitely you gain gravitational potential energy because you were higher than your starting position. So there's always an event or a change. Like for example, now the change is I climb up the staircase. But anybody know where this energy come from? Because all energy you cannot create one. All the energy that we have always had since the beginning of time. Energy cannot be created, energy cannot be destroyed. So this GPE is converted from another form of energy. What do you think this energy is? 你爬楼梯, where the energy come from? What do you think? It cannot come from nowhere. Chemical, very good. In your muscle, teacher, I learned in bio, my mitochondria do some magic fancy thing that Miss Lee, the physics teacher, don't remember already. Chemical energy. That means Amina actually have to use her muscle that converts the food that you eat using some biological process to go from chemical energy to gravitational, gravitational potential energy. Okay, so very quickly, there are certain types of energy that is important, and then there are certain types where we just want you to got this energy one, but actually 没有这么重要啦, because the calculation is not very straightforward. If the calculation is straightforward, then we will include it in your syllabus. But we want you to be aware of these energies to begin with. Okay. And then I'm just also going to give you some different values. Okay. So here, there are different types of energy. I will rank them by popularity. Kinetic energy, very popular. I give you a 3-star. Because the whole chapter is study movement, 动的东西就有 kinetic energy. So any kind of object that is due to motion. All moving objects have kinetic energy. You move faster, you got more kinetic energy. For example, the kinetic energy of a football, when you kick it, it's about 50 joule. All right. Potential energy is the energy that object has because it changes its shape, state, or position. Now, potential energy is too general. We got a few types of energy. So I'm not going to give you any star because type general already, don't know. So first type of energy also gets 3-star, your gravitational potential energy. This is due to the position of an object. Let's say I stand on my chair, or I stand on my table, or I stand on my floor. Of course, if I stand on the table, I have the most GPE. Okay, and then physics teacher tend to use short form now. So kinetic energy 我叫 KE 咯. Gravitational potential energy 我叫 GPE 咯. Okay, so a stone held up in air can do work when dropped because gravity will pull it down. So this is due to position of the object. The higher the better. Okay. Elastic potential energy also gets 3-star. Okay, but we also sometimes call it strain energy. So a stretched rubber band can do work when it's released. So for example, when you compress a spring, it has elastic potential energy. When you stretch a rubber band, it has elastic potential energy. If you exercise, you trying to work out and stay healthy in the pandemic, although you sit at the table for 8 hours a day, maybe you use the exercise band or you stretch the exercise band. Elastic potential energy. You know, and the band that I see people exercise one. Maybe you lift weights, you lift the dumbbell, you know, you want to get nice arms. When you lift the dumbbell, you are doing work against gravitational potential energy because you're lifting something that is heavy. Your force is the one that is doing the energy conversion from the chemical energy in your muscle to gravitational potential energy. But fun fact, do you know that the muscle has also elastic potential energy? Because your muscle can stretch. Let's say, for example, you want to jump. I ask you a question. Do you jump with your legs locked? Like, what is this drawing? Do you jump with your legs like locked like this? Everything is locked. Or do you jump with a, you know, you bend your knee, you squat down a bit, then only you jump? Which person jump higher? You lock your joints, you lock your knee, you lock your ankle, and then you jump. Or you go down a bit, you squat down a bit, and then you jump. Of course, teacher, you bend knee lah. Of course, you know why? When you bend your knee, you shorten the length of your muscle. You shorten the length of the muscle on your leg, on your quads, the muscle in front. You shorten the muscle at the back of your leg, your hamstring. You shorten the muscle that helps you jump and stabilize, which is your butt, the muscle on your butt. Okay, so all this is storing elastic potential energy in your muscle so that when you jump, it's like you are a rubber ball or a rubber band. Whereas if you don't bend your knee, then you not so high lah. Okay, so these are very important. Has calculation, has equation. So these are other examples of values. The values are not really that important. So the gravitational potential energy of a skier when it's jumping, chemical potential energy. So if you look at a cookie, it has chemical potential energy. Haven't eaten yet. So unless you eat it and your body digests it, this is the energy released by chemical reaction. Energy stored in the field is called chemical potential energy. Or sometimes we just call chemical energy. Battery also got, food also got, and without chemical energy, your muscles will not move because it just cannot. It needs to have something to burn. You play Minecraft? I play Minecraft. What is Minecraft's source of energy? Minecraft have a lot of chemical energy. I give you one now. Coal. You go get the coal, can make torch, can cook food. Lava. Okay. Food, I eat the chicken, correct. Okay, so all this is chemical potential energy. All right, electric potential energy. No stars. Just need to know 有这个东西就可以了. No need to calculate one. This one all need to calculate. Got equation. The one that I star. I guess maybe 1 star, because sometimes you need to mention it. Okay, electric energy. In circuit, electric potential energy. The current is a flow of tiny charged particle called electron. Again, if you play Minecraft, this is called redstone, right? Redstone help you like empty a dispenser without you having to go and do the work. Or the electricity in your house help you rotate the fan that is blowing you right now without you needing to go and like 自己 manually 转那个 fan, so tired, okay? So the current is the flow of tiny charged particles called electron. So when the electron flow, the electron is like very cute one. I show you a picture. Or rather, I show you this comic that someone drew some time back that I then borrow. That will be this one. So your electric potential energy, let's say you have a circuit like that. This electric potential energy, 它收到 energy from the chemical cell of the battery. Okay, your Duracell, your Energizer, you give the electron energy. The energy is like post laju. The electron takes the energy and then carry here. So at this point, right, electric potential energy is converted to kinetic energy so that the electrons moving in a circuit in a fixed direction. So it's like when it passes through the battery gives the electron a boost by giving it chemical energy, and the chemical energy is then converted to kinetic energy. So the electron boost, supercharged, pass through the resistor. So when they pass through the resistor, imagine the resistor, right? It's like an obstacle course. They will collide with the atom inside the resistor, bing, bing, bang, bang, bang. And then it will surrender 6 joule of energy to the resistor. Okay, I lost 6 joule. And then I go through the 8 ohm, I lost another 4 joule. 12, I lose 6 ma. 8, I lose 4 law. All can use ratio one. Are you very smart one? Now 4 ohm, you lose how many joules? 2 law. So every time I lose all my energy. So think about this. What is 6 plus 4 plus 2? 12, correct. So by the time you come back, you get another 12 joule of boost. And then you come here and then you waste all your energy. So what the electron does is that it takes the chemical energy from the battery and then it transfers the chemical energy to your resistor. But what is resistor in your house right now? Maybe the first resistor can be represented by your fridge, because your fridge uses electricity to turn on the fan and cool down the air. Maybe the second resistor is the kettle used to boil water to drink your Milo. Maybe a third resistor can represent, I don't know, the light. Your light can be hot, your computer. So the electrons, or basically electricity, we say that they all have electric potential energy because in circuit, the current or the electron, okay, these tiny particles, electron, they transfer energy. They're energy transferer. They are the UPS, the post laju. What else? The JT Express. So you're going to transfer from battery to light bulb. Okay, so we call it electrical energy or electrical potential energy. But for this chapter, it's not that important. I'm going to give it 1 star because later we will study circuits properly. So later in circuits, in year 11. But just know, got this energy. And then there's another energy called nuclear energy, nuclear potential energy, because In the atom, there is a nucleus at the center. So it's made out of particles, okay? And when we split the atoms apart or split the nucleus apart, we get energy. So the nuclear reactor is when I take the atom, 我切一半的 energy 就出来 because 一半比较 stable 啦, okay? So this one is also year 11, but just so you know, that's energy. Comparing the amount of energy, right? There are certain things which have a lot of energy. Right? For example, chemical energy in petrol, a lot. Chemical energy in the food that you eat in one day. Wow, teacher, I need so much food one. I need so much energy. Yes. Do you know where this energy goes to? You think about it, football only 50 joule. 煲水 also this little joule. Why do you need so much energy? Any guess? We eat a lot of food. It's a lot of energy to maintain, to feed a human being. What do you think the energy is used for? Any human being, this is not athlete, just like a regular person. What do you think the energy is for? 给谁用的? Used for what? Any thoughts? Any ideas? What is the energy used for? Every day you eat so much food. What is it for? Feel your body. Why does your body need that much energy? Any thoughts? Random guess. I guess I'll ask you a question. Is your blood warm or cold? Warm. Okay, very good. What warms up your blood? Teacher, are you saying that I eat the food to warm up my blood? Yes. Yes, that's why you eat so much, to keep your blood at a nice 37 or 36, 37, 36.9 degrees Celsius. So certain animals like amphibians, crocodile, snake, they don't need to eat so much one. Occasionally they come out and swallow the whole rat, and after that they chill for 2 weeks because their blood is cold. So cold-blooded animals is an evolution adaptation to not needing to eat so much food. But we mammals, 讲了名字都是 mammal 嘛, mammal is warm-blooded. You think about your sciences. So we need the energy to maintain our body temperature. In fact, if our body temperature falls below a certain amount, we'll die. Okay. We need the energy to breathe. So the whole respiration process actually warms up your body. Okay. So yeah, like that lah. Can. So mainly is to just maintain your body temperature. That's all. So if let's say you have a very lazy day, if cold-blooded animal blood become warm will die. Yes, they will die. Because their whole system or their respiratory system, their digestive system is adapted to cold blood. You suddenly warm up their blood or GG cannot. It's a bit like our digestive system is adapted to warm blood. If our blood too cold, too hot, or GG. You got fever that time, you can eat or not. Your fever 39 degrees Celsius are also you like, I cannot eat, I just need to sleep. Can kill snake with ginger juice. Ginger juice very hot, man. The mouth. Okay, anyway. To maintain your body temperature. So if you lie down on the bed or you never do anything, you just lie down on bed and you sleep the whole day, you still need at least 1,004 kilocalories, which is basically still a lot of energy to keep you breathing, to keep your body warm. Yeah. Speaking of warm, these are some terms that we use to describe warm or heat or thermal energy. Okay, so there's thermal energy. And thermal energy is actually a very interesting form of energy because this is due to the atoms and molecule, their vibration. Okay. So any form of vibration, there is thermal energy. Currently, we are all vibrating. Our particles are all vibrating. 37 degrees Celsius, all your particles are vibrating very happily. You have thermal energy. Friction will lose as thermal energy. Another type of energy is like the light energy or the sound energy. So radiated energy like sun and sound and waves. So this is mainly for wave. And wave is also in a later chapter. So maybe we're going to focus on this one. This one can be due to friction. So it's the energy loss to friction. Energy lost to friction. So in a nutshell, what is important? Gravitational, kinetic, elastic, if you have a spring or rubber band. And if you lose energy because friction, then heat loss less heat. Okay, time to do some practice to see if we get the main idea. All right, so I'm gonna try this method where I will do a poll. I'm gonna do a poll, and then I just want to see whether you're okay or not. Anyway, and you can answer the question. Anyway, let me show you the question first before I post up the poll. Okay, we're gonna start very easy. So, question 1. Is ginger juice hot? I need to go and try this hot ginger juice. Okay. I set up a poll. What do you guys see? I don't know. I'm trying this Zoom thing. I mean, I can use Menti or Padlet, but a built-in try is out. So do you have a poll? Maybe you can. No, does it work? It's loading very long. Yeah. Okay lah. Then never mind lah. It's okay. We can do the question. When it loads lah. If not, I can try other stuff. Okay. So energy, if it loads very long, just leave it. Don't worry about it. So energy resource, obtain electricity without producing heat to boil water. So I don't want any heat. Coal, I heat up the coal boil water, the water rotate the turbine. Gas is also heating. Nuclear is very hot one. You see the nuclear power plant? Okay, so the only one without producing heat to boil water is C. Hydroelectric, or another form is wind. Okay, so to obtain electrical energy for A, B, and D, we will boil water and then the steam will rotate the dynamo. So this is the start of the steam engine. Because when we rotate the dynamo, we can generate electricity. How does it work? That one is also a bit later. We will revisit this again. Okay, but that's the whole idea. So speaking of that energy resource, right? Here is basically how a hydroelectric system look like. Okay. So you have a reservoir up here where all the water is inside. Okay, and then the water will flow down into the power station. And then in the power station, the water will rotate the dynamo. Okay. So what are the main energy changes taking place? So if we think about the water is at high level, right? So there is a drop in gravitational potential energy. Yeah. Okay, very good. So then you got C already. But as GPE decrease, you imagine now 水流下来, it will flow faster and faster. So at this point, KE will increase. Okay, so GPE to KE. And then at the same time here, in the power station, I will convert kinetic energy to electric energy by using a device called a dynamo. Not the 漂白剂, but just a regular old dynamo. Okay, I guess the last one is this one before we go and do some calculation or equation. So we have my dude here. He is going from X to Y without pedaling. Travels down the hill from rest at point X without pedaling. The cyclist apply his brake and stop at Y. So when we apply brake, by the way, you travel down the hill from rest, it means that you have GPE because you're at a certain height. Very much like the water, as you travel downhill, you will go faster because of gravity. So GPE become KE. But at Y also stop already, meaning 我踩 brake. If I apply brake means I increase the friction between the wheel of the bike and the road. Okay, that causes heat or thermal energy. So the answer is A. Very nice. Okay. Okay. Plot twist. This is collision, teacher. Yellow. A gas molecule strikes the wall of a container and the molecule rebounds. Boing, boing. But it rebounds with the same speed. Meaning if this speed is, I don't know, 100 meters per second, and then you go back, it's also 100 meters per second. What happens to the kinetic energy and what happens to the momentum? Do they stay the same? Do they change? They both change. They both stay the same? Both change? Okay. What about the others? What do you think? momentum is, after all, should get you to vote. Let's see. What about the rest? Do you think that momentum will change? Do you think that kinetic energy will change? Okay, first things first. I'm pretty sure that kinetic energy will stay the same, because kinetic energy is due to motion. And then the quantity that represent motion is 100 meter per second, same speed. Okay, and the mass is the same. So the object didn't become more massive, requiring more energy. Makes sense, right? If you have a light, if you want to push a bowling ball versus you want to push a tennis ball, of course, the bowling ball will need more energy. So motion, mass, the same. So this one should be the same. Okay, what about momentum? Remember when we discussed the rocket just now, momentum P, although is equal to mv, but this momentum is a vector. And this is a scalar. So scalar quantity 是没有 direction. 没有 direction 就不用理咯. But this one, it did change direction. It went from towards the wall to away from the wall. So the reverse in direction means the momentum already changed. Reverse direction. So the answer is C. Both, it's not both stay the same. Both magnitude stay the same. But because momentum 不只是 magnitude 嘛, momentum 还有 direction. 它 direction 已经得balik了. Okay. So, yeah. That lah. Right, here's a K-Butt question. This one is quite K-Butt. So it's fun. Momentum can say from positive change to negative. Yes, that's why they change. So maybe from positive 100 to one direction become negative 100. Because whenever you see a vector, 它有可能两个东西换. Either 它的 magnitude means the size change. So maybe from 100 to 80 or 100 to 120. Or it can be direction change. Because vector got both magnitude and direction. But for scalar quantity, it doesn't have direction, only magnitude. So the magnitude stay the same because the speed is the same. Now, here's your K-Butt question. Energy resource does not derive its energy from the sun. Okay, this one, everyone, please answer. If you don't answer, you just tembak lah. You're very good at tembak. Which one doesn't come from the sun? Teacher, any of these come from the sun? We have an answer, A. What about the rest? Matthew, what do you think? Gahe, what do you think? Ziyu say it's D. Interesting. Does not come from the sun. What? C. Okay, Gahe, you put B, then everybody choose one different answer. Got A, got D, got C. Not from the sun. Let me eliminate a very easy one to eliminate first, which is what causes waves and what causes the wind? If you think about it. Wind is due to the heating of different parts of the atmosphere. So for example, when you go to Port Dickson, whenever we can go to Port Dickson again. Okay, let's say you go to the beach. When was the last time you stood beside the beach? I also don't know. So I don't know whether you relate to this experience or not. Let's say you stand beside the beach. Maybe around 8 p.m. will you feel the air blowing to your face? Or do you feel the air blowing away from your face? Mm, 我去海边吗？你站在海边，晚上的时候 after dinner, the wind blow towards you or away from you? Or you just don't know, teacher, what is beach? I'm a pandemic baby. Okay, so yeah, I just don't know. Okay, next time, hopefully soon, if you get to go to a beach, okay, or a large body of water like a big lake, cannot be a small pond, okay? Swimming pool cannot, pure water. So water can hold heat very well. So at night, 8 p.m., the water is slightly hotter. The air here is hot. And then the land doesn't hold heat very well. So the land is cold. If you think of your geography, right, people always say 沙漠很冷 at night, correct, lor, because cannot hold the heat. So the wind will blow from hot to cold. You stand beside the stove, don't you feel that the hot air is blowing towards your face? You cook food. This is because hot air is high pressure. Cold air is low pressure. So the hot air will blow the cold air. But what causes the hot and cold to begin with? Nah, our abang matahari, the sun. So heating of different parts of the atmosphere. Causing airflow from high pressure, the place where you heat up a lot, to low pressure. This also causes waves. Okay, it's the same idea. If the pressure difference is big enough, the wind that blow on the sea will cause the wave. What causes wave in the first place? Wind blowing. Strong wind in the middle of the ocean, blowing the water causes wave. Okay, now you're left with these two. Why do we have 瀑布? Why do we have waterfall? Because we need to hydroelectric. Or rather, I'm just going to ask you, who fill in the reservoir here? Who add the water? What add the water? Sure, this one need to ask me. Got rain rain. The rain fall down, then I collect the rainwater lor. You know this thing called water cycle? Let's say this river in the end go to the ocean or a lake, and then we have the sun. The sun will heat up the water will evaporate, and then it will form clouds, and then the cloud will rain, and then the water cycle repeat itself. Oh, so no sun, no water cycle, is it? Yeah, no sun, no water cycle. So the sun initiates or basically keeps the water cycle going. Do you know without the sun, we are just, you and I, we would die, my friend. We will stay alive for a few days in absolute horror. Okay, like the sun is still there, the gravitational attraction is still there, so you're not going to fly away into outer space. But we'll die. It'll be so cold. Sun keeps the water cycle going, and it refills the reservoir. How to spell reservoir? R-E-S-E-R-V-I-O-R. Okay, so the only thing you have is fusion. Nuclear fission, this one is as long as I can find the nucleus that is radioactive, whether it's uranium or lanthanum or any of those high-tech things, I don't need the sun. The sun doesn't cause the nucleus to split apart. Okay. So this is independent. Independent means not related to the sun. This is 所謂的奇物啦。Okay. Now, we are going to look at the first calculation scenario where we can calculate these values actually. Okay, so we're going to look at we have to understand energy transformation. Okay, so I'm just going to give you a few examples that is readily available in your textbook. For example, we have discussed this before. Let's say you throw a ball or a stone, I guess. So you have energy, chemical energy in the muscle, and then the stone move upwards, so it becomes kinetic energy. And then the stone at the highest point becomes potential energy. Stone fall to the ground, go back to kinetic energy, hits the wall will vibrate. Okay, the vibration is thermal energy. So all of this is following the conservation of energy, where your energy cannot be made or destroyed, but can change from one format like chemical energy to another. But every single time, the transfer is not perfect one. So whenever I transfer, 我会流失一点 energy. So there's always somehow a loss in energy. Okay, so here's what you may have seen before in your year 7. We call it the Sankey diagram, but it's just a flow chart, okay? So this is all the chemical energy that you makan every day. I eat this food. Sure, I eat a lot, like I mentioned, we all have to eat a lot. And then a lot of it is wasted in the body. This much, teacher? Yeah. Okay, we don't call it wasted, we call it like metabolism. So if you like look at your friend, teacher, he can eat 3 plates of chao kway teow, still so thin. I eat 2 tauge, I gain 1 kg because this wasted energy a lot. You are very energy efficient. You don't waste energy. Okay. So let's say that few seconds, right, that you throw the ball, that 1 or 2 seconds, your body already use a lot of energy to maintain your body heat. Metabolism. Fun fact, your friends who are very thin and eat a lot, but still thin, they always sweat one. They sweat a lot. You may think, teacher, I also sweat a lot because I'm very fat. Yeah, that one you sweat a lot because you cannot. Fat is a very good insulator. But skinny people, they also sweat a lot, especially those who eat a lot. Metabolism very high one. It's because their body runs through the energy very fast. Okay, and you right now, a lot of your your energy is not wasted, like it's also used to grow. You are still growing, right? Growing taller still, hopefully. I don't know. I also don't know. Puberty. Okay, I want to point out something. You will only properly stop growing at around 23, 24. Like mid-20s. Now, don't get so excited and think that you may grow taller because that's the physical growth. But your brain is still in the process of getting smarter. So how you see the world and how you form your knowledge at this time is actually a very crucial one. Not that you have to be the smartest cookie in the class. You just got to know that you are working towards something. All right, anyway, some of it will transfer to kinetic energy to the stone. But then you look at this one, some of it is wasted because of air resistance. So when the stone go up and come down, there's air resistance. And some of it is wasted as sound when it collides the ground. And then some of it is thermal energy in the ground and the stone because the ground and the stone will vibrate during that collision. So at every single point when the energy transforms, right, there is work done. Okay, so it's important to understand that to think about energy or work done, that work done is energy transfer. So for example, I throw the stone, I got 20 joule of chemical energy in my body. Okay, and then my hand exert the force, pushes the rock. that is the force that causes the work done. Force work done here is force times distance. Okay. And this 20 joule of energy in another form can be kinetic energy. If this is perfect transfer. Okay. Another example is, let's say I'm dropping a rock like this. So if I drop a rock or a brick, I have 20 joule of potential energy. I convert to 20 joule of kinetic energy. But teacher, who is doing the work? You pull down here. What is the force that is acting on this block? Surely it is weight. Gravity is the one that is pulling the block down. You also can explain it in your brain. So this mg here, right? This one, when we have this energy transfer, here I will write work done of 20 joule by gravity. So this W is actually equal to force of gravity times, maybe I call this distance h lah, times h, times distance ma. So the force of gravity is mg times h. Okay, and this work done actually equals to the kinetic energy. And this one will be equal to 20 also. So 每一次有 transfer， 你是需要一个 force， 那个 force 呢就会做 work. Whenever there is work, there is energy transfer. That's the main takeaway. And of course, after that, the 20 joule will be thermal energy. And thermal energy is just, normally thermal energy is the end of the road lah. It will disperse as vibration inside the molecule and then 就不见了, bye-bye. No more energy. Okay. So, let's see. Okay, we're going to look at a slightly complicated example. Slightly, don't be scared. Which is this one. Okay. And so here we have a mass M. Okay. And it's going to slide down the slope. So your UPS guy, you want to deliver the 11 shopping that your parents buy. I don't know what they buy. Mixer. Lawnmower. Okay. So we slide the box is sliding down the slope. Wow, they even tell you slide down the slope of length L. So distance from here to here is L. And vertical height D. And then there's also frictional force. Sure. It loses GPE. And it does work against friction. Which role give the loss in GPE and work done against friction? Loss in GPE, right? Again, there is always Fs here. So when you see gravity, 你直接就可以知道你的 force 就是 gravity 的 force 就是 mg. Okay, let me zoom out. So for gravity, W is equal, work done is equal to Fs. But because it's gravity, so this one must be mg. In fact, you see everything is mg. What is the distance traveled? Remember, mg, whenever we use the equation, work done is force times distance. Did I use Fs, Fd, anything lah? Force times distance. F and D is parallel. F, D, parallel. So if I look at the mass, there is definitely mg, weight pointing down. So I should take mg that is pointing down, and this is the vertical height that is pointing down. So GPE, the change or the transfer in gravitational potential energy will be equal to the force of gravity, which is mg, and the distance traveled is d, because these two is parallel. So we want mgd out, only these two. So then I need to decide work done against friction. So who is the force here? Work done is equal to force times distance, but this force is now frictional force. Previously, the force is gravity. Where is friction, teacher? Nah, frictional force here. Okay, which distance is parallel to this F? L. Can see L is parallel to F. So I can say work done is force times distance, but work done against friction is equal to the force times L, because F and L again parallel. So 这个只是看 direction. So although the question look very complicated, but actually it is not. Whenever you look for work done, always remember to take the force multiplied by the perpendicular distance. Okay, so one last one before we go. Force multiplied by the parallel distance. Perpendicular distance is the moment one. Okay, a student, last one, carries out a simple exercise. Which exercise is the most work done? Teacher, I eat too many plates of chao kway teow now. I need to burn some of the energy. Okay. Which one you will burn more energy? I give you equation. Work done, WD is force times distance, but force must be parallel to D. Which one? Which one will give me the most work done? Okay, so yeah, you think about force times distance. Then you go like, I lift 1 kg 1 meter. So maybe here to here lah. Here to here is 1 meter. What is the value of this force? This force must full this 1 kg, right? Must support this 1 kg. So this upward force must be the same as your mg, which is 1 times 10, which is 10 Newton. So then this upward force that is lifting, the student's hand that is lifting, this is also 10 Newton. They only can lift, right? If not, then you're not strong enough, no? So in option A, the work done is 10 times 1, which is just 10 joule. Teacher, I eat so many 1,000 calories then. So many 1,000 joule. Okay, chill first. This one, again, work done is Fs. But now we move, or FD, we move 2 meters. And the weight is 2 times 10, which is 20 Newton. So I'll put 20 here. This is 40 joule. Okay, so I highlight for you. I take this force multiplied by this distance, come as a parallel. I take this force, which happens to also be 20 Newton. Otherwise, what you live for, you leave nothing. Okay, then I multiply by this distance, which is 2 meters. Okay, so far C is the winning companion. Okay, let's look at B and D. B, I push 1 meter against 4 Newton of friction. Means my force is 4 Newton. My external force, all external force, I put green color. So I push 4 Newton so that I can overcome the friction of 4 Newton. You see now, for all of this is the same case one. 2个 direction of force 要一样 so that it will start to move in with the same speed. Okay, So you want to use work done is force times distance again, but currently your force is 4 and your distance is 1. So this is 4 joule. So this one, this one you push 2 meter, 2 Newton. Work done is force times distance, so 2 times 2. 4. This one here to here, 1 meter. Here to here, 2 meter. So you can see that this force, this force and this distance is parallel, 4 times 1. This force that is working against friction, and this 2 meter is parallel, 2 times 2. So the answer is actually C. It is more work to lift something that is heavier vertically upwards than to push something that is heavy. Quite logical. Okay. And maybe B, the ground is rougher lah, so the friction is 4 Newton. And maybe D, the ground is smoother, so the friction is only 2 Newton. So the external force that you need to apply is 2 Newton, whereas the external force that we apply here is 4 Newton. Okay. That's it for today. So what we have really learned, we have learned that there are different types of energy, and whenever there is energy transfer from one form to one type to another type, there is work done, and we can calculate the work done using force times distance. Be very careful to make sure that force and distance is parallel. Also finish your impulse work, okay? So to refresh your memory, I will probably give you a few objective questions to try regarding this whole idea of work done is energy transfer and types of energy. Just MCQ. So try them or fill up the form if I create a form. If not, you just try them first before I'll see you next week. But we continue about energy conversion and also equations about actually how to calculate kinetic energy, which is also from this one. But master the basic first. W is force times distance. Force and distance is parallel. All right. Any questions, my friend? If no, then I let you go lah. Enjoy your dinner. Have a good rest and weekend. And thank you. For those of you who reply in the chat, see. This actually that I'm teaching a student. All right, I'll throw this into Google Classroom. See you. Take care. I was chill a bit if you want to talk to me or ask me stuff, but if not, then bye-bye lah. Thank you.
Thank you, teacher. Bye-bye.
Bye, Miss Lee.
Welcome. Bye-bye.